It's 10 o'clock, so I guess we should start. Welcome everybody to this GBADs DECIDE webinar series. In this series we have 3 speakers. Please make sure your microphone is muted during the talks. We will first do the 3 talks, and then there will be time for questions. And if you already have questions in between, then please put them in the chat, and we try to answer them at the end of the 3 presentations. I will briefly introduce the speakers in between, and it's a nice mix of people from GBADs and DECIDE as always, and we'll finish. We try to finish in an hour at 11 o'clock. So the first speaker of today is Professor Ilias Kyriazakis. He's a professor of animal and veterinary science of Queen's University in Belfast. Ilias, the floor is yours.
Good morning, everybody. Can you see my screen? I have just shared it.
Yes, but it's not in presenting mode yet.
Yeah, thank you for that. Okay, thank you very much for the introduction and the invitation. I am going to present today the outcomes of a collaboration which resulted in this paper you see here. The paper was published 7-8 months ago, and it was the result of locking in 15 people and not letting them out of a room until they produced something after 3-4 days. Okay, so why an open goal? What is the link of animal health to emissions, and why did we consider it an open goal? We considered that because the animal health has consequences on the efficiency of a system, okay? And by definition, emissions arise from inefficiency. So if you have something that is not captured by the system, either in the products or in the animal itself, then it is excreted in the environment and it is emissions, okay? So as you know, animal health has several consequences on animal outputs. It can affect animal growth, so the animal grows more slowly, it is less efficient, it can affect its outputs like milk, meat, or the product quality. It affects its reproduction capacity, so you have more abortions, the animals start reproducing later, and of course you have a lot of waste, either because of culling or because of mortalities or condemnations. Okay, so we have all these inefficiencies, and intuitively you would expect that animal health will be affecting emissions. Now, all these effects of animal on animal outputs or on animal functions are carried through changes in the way that the animal capture or deals with energy and nutrient quantities. So what does it do? What does disease do to the animal functions? It increases its maintenance functions because you might, for example, have an immune response or you might have resources directed to the repair of damaged tissues. You might have a decrease in feed intake, and it's a very common factor in most diseases. We have what we call pathogen-induced anorexia. Then downstream, once you have consumed the feed resources, you have a reduction in nutrient absorptions because, for example, the gastrointestinal tract might be damaged. You have changes in nutrient utilization, so how the nutrients are partitioned in the body, because you might want to partition things towards the immune response, for example. And the consequence of that is that you have changes in the body composition, and you also have changes in the manure amount and composition. So it's very clear how disease affects emissions. Unfortunately, when you look at the evidence that links between the two, the evidence is not very strong. And I would like to put to you that this is because of two bottlenecks. The first bottleneck is that it is difficult to incorporate the effect of disease within an emissions framework, because of course it's always very difficult to make direct measurements for the consequences of disease. Then you have complex interactions between health conditions. Usually you don't have a single health condition, but you have co-infections. And then most of the data you might have available might be in experimentally infected animals, if you are lucky. Then there is the challenge of the scale and the boundaries of considering the effects, given how diseases are spread. Obviously, whether it is the pen, whether it is the room, whether it is the whole farm, whether it is a cluster of farms, all these things need to be taken into account. However, quite importantly, we don't have linear effects between health challenges and consequences. And on your right-hand side, you can see one example that comes from my work, which is the relationship between infection and the food intake. And you can see that clearly, and this is very typical of many diseases, the effect is certainly not linear. Initially, the animal tries to cope with the infection. Then you have a reduction in the food intake for a wide range of infectious challenges. And then you have almost a catastrophic effect, as it's called. So it's clear that this effect is not linear, but it's also clear that it's not a unique relationship. And then we don't have a linear relationship between health and emissions, and I'm going to get into that into a little bit more detail a little bit later. The second bottleneck is how do you link a health challenge, how do you link a health condition like a disease to disease consequences? So that is the second challenge, because as you know, you have quantities that are excreted, and then you really need to translate these quantities, and these quantities are either energy or nutrients excreted, and you need to translate them into how they affect activities, the activities being, for example, the global warming potential. Okay, and as I said earlier, here I have taken the example in all cases, the problem of emissions is a problem of energy or nutrient balances. Yes, so anything that is not kept in the animal is emitted, through respiration, or it's emitted through the feces. Okay, now the problem is the emission factors in order to link these two. So how do you translate the emissions, as I said, to the effects of these quantities? And people are using the emission factors according to the IPCC methodology. I apologize to the people who are already familiar with the methodology. But for those who are not, the most important issue is that there are three types of emission factors. In tier 1 is the most simplistic. There are book values that are based on international emissions. So you have, for example, emissions in the Netherlands from cows, so you take this into account. And tier 3 is the most detailed emissions. This needs to be taken into account when you are talking about emissions that result from disease and they are converted into activities, so global warming potential. Now, when you are looking at the emission factors that relate to animal health, again, you have these three tiers. And the first tier, if you are using the first tier, it effectively accounts about animal numbers. So if you have a disease, for example, it reduces the productivity, then you need more animals to have the same amount of output. Tier 2 is a little bit more comprehensive. It takes into account the animal performance, but it also takes into account what kind of feed you give to the animal. Because obviously you will not be feeding all animals the same, which is the assumption of tier 1. And then you have tier 3, and the tier 3 is the most comprehensive, as I said earlier, and this takes into account the consequences of the disease on digestion and metabolism. And this is, as I said, very important because diseases affect the processes of digestion and certainly affect the processes of metabolism. Now, when you're looking at the literature, there is no real evidence about tier 3 to link disease to tier 3 emissions. So what is the current state of the literature? In our paper, we reviewed comprehensively the state of the literature, and really the only evidence that exists experimentally, the evidence is on sheep challenged with gastrointestinal parasites. And there are around 10-15 studies that did that, and only 2, surprisingly, only 2 show that there is an expected increase in emissions if the animals, one case in lambs and the other case in ewes, are infected with parasites. On the other hand, and this is what people are talking about, there is a lot of evidence from modeling studies which suggests that there is a link between emissions and disease. And the evidence is again on gastrointestinal parasites, but also on intracellular parasites like trypanosomes, but also syndromes like lameness and mastitis. But if you look at the studies on modeling, there is no quantitative agreement between these studies. So it's very, very confusing. So now what we did as part of this exercise, we considered a very simple syndrome. The syndrome was mastitis. And we considered a herd of cows with a given incidence of mastitis. We took the Netherlands, was an example. And then we applied the effects of the mastitis on herd productivity. And then we considered the emission factors either in tier 1, tier 2, and tier 3. And this slide gives you a very, very good example of what is going to happen. The first issue, which is not surprising, other people have said that, is that if you are using tier 1 factors to estimate the effects of disease, you consistently underestimate the consequences, which is fine. Interestingly, if you are choosing tier 1 emission factors, the difference between the healthy and the non-healthy status is the greatest. Now, if you are using tier 2 emissions, the effect of mastitis with that particular incidence, I'm not saying that this is the case for all mastitis effects, in this particular case is around 3%. Now, interestingly, we chose specifically mastitis because mastitis does not have any effects on digestion and has very small effects on metabolism. So we chose it specifically because you were able then to use a rumen digestion model to estimate. And you can see that because of this particular example, the difference between using tier 2 and using tier 3 emissions is not really huge. However, if you have a disease that affects the gastrointestinal tract, the outcomes that you get between tier 2 and tier 3 emissions are very different, and the conclusions that you draw are also very different. Now, despite this lack information in the literature, this has not stopped people making calculations through modeling. This is a study which is now 10 years ago. This assumes that the relationship between health and emissions is linear, and it also uses actually tier 2 emissions. Now, you should be able to estimate the disease impact if you are using tier 2 emissions, but as I said, you should never use tier 2 emissions to estimate the consequences on mitigations, because mitigations change a lot of things and the change is not linear. And the other thing which is also quite important is that if you stack mitigations, the effects of mitigations themselves are not additive. And yet, this has not stopped the people to do that, which is a little bit disappointing. And then, of course, people have gone a step beyond that, and they have used tier 2 emissions to estimate the relationship between mitigations of animal health on emissions and how this relates to the cost of these mitigations. And this is a classical MACC curve, but this study has largely discredited because, as I said, you should not be doing this kind of things, especially in this case, because there is a stacking up of interventions. I'm not very sure which is worse, whether it is the people who have done this exercise and they have done clearly motivated by the desire to make these calculations, or actually the people, or it's the mistake of the people who refer to these studies, and you see it in the literature, this study and the study I showed previously, that they refer very, very extensively in the literature, although they have never been peer-reviewed. Okay, so now the gloom, up to now I was a little bit pessimistic. Now, what is the way forward? In the paper, we suggested a roadmap of what we need to address to link animal health to emissions. I appreciate that this is a little bit of a complex graph, so I have distilled it so to make your life easier. And this roadmap that we produced in 24 is actually very similar to what I had suggested in 21 with my colleague Stephen Mackenzie. Of course, that's expected because I was an author in both exercises. But the first case is that epidemiological models for several animal health challenges exist, and the challenge is to modify them for different scales. This knowledge should allow us to progress and estimate the impact of a variety of diseases on greenhouse gas emissions, because information on the effects of disease on animal outputs and efficiencies on a variety of cases can be streamlined. If you look in the literature, you can find it, although some refinements may be desirable. What is lacking, and that's what you were calling, is the understanding of animal health on feed intake and the utilization of nutrient and energy resources is lacking, and this greatly inhibits our ability to estimate, for example, methane emissions from feed conversions, but also emissions beyond methane, because there are other greenhouse gases like nitrous oxide we should be accounting for, and people usually ignore them, and that's why FAO has recommended to look at that. Now, if we had that, if we had the third bullet point, what else would we need? Well, then it's the icing on the cake. So this is the second, probably, things that you want. So we need to account for the effects of animal health on product quality. Then, as I said, and FAO is very, very strong about recommending that, we need to consider environmental impacts both beyond methane and beyond greenhouse gas emissions. So we need to consider effects in eutrophication and acidification potentials. And then, and this is in the context, and I suspect that's why the invitation was here, we need to integrate economic considerations to produce recommendations for the most cost-effective mitigations and produce decision support systems. So thank you very much for your attention.
Thank you, Ilias, for your nice and interesting presentation. It's always more complicated than you think beforehand with the non-linearity. I'd like to announce the second speaker of this morning. It's Dr. Mayberry. She's the Principal Researcher Scientist at Commonwealth Scientific and Industrial Research Organization in Australia. When you're ready, Di, the floor is yours.
Thank you. I'm hoping my screen is sharing correctly. Yeah, wonderful. And thank you for the invitation to speak this morning, and also to Ilias, who I think has really set the stage for what I'd like to chat about today. So I'm going to share with you our experience of trying to quantify greenhouse gas or changes in greenhouse gas emissions associated with improvements in animal health as part of our Global Burden of Animal Diseases case study in Indonesia. So this work is presented on behalf of my Indonesian colleagues, Ibu Yeni, Pak Tatan, Pak Takin, Ibu Yeni, Ibu Indi, and Pak Harimurti. And they're the ones who've done all of the hard work, sourcing data and running these analyses. I'm just the one who stands in front of you all. So this case study was funded by the Australian Centre for International Agricultural Research, and it was conducted in partnership with BRIN, Griffith University, the University of Gadjah Mada, PT Mitra Asia Lestari, and with support from the Global GBADs program. Since this seminar is part of the regular GBADs DECIDE seminar series, I've made an assumption that most people in the audience will have at least some knowledge of the GBADs program. So I'm not going to spend too much time talking about GBADs and what we do and what our methods are. Instead, I'll give you a brief introduction to our case study in Indonesia and go through the why and the how of trying to include greenhouse gas emissions into our analysis as a bit of a test case for future GBADs case studies. So the main aim of our case study was to pilot the GBADs approach in Indonesia and build capacity within our research teams. So there's a global GBADs team that are the ones who are developing all of the methods, and we wanted to see how it would work in a different country, different production systems, different data ecosystem, different capacity levels. So Indonesia is spread out across 38 provinces. There's over 17,000 islands, and livestock are kept for food, for economic purposes, and for social cultural reasons. Rather than us trying to account for this vast diversity of production systems and estimate the burden of disease for the whole country, like has been done in other case studies, even for just a single species, we decided to focus on a few specific regions and production systems in this initial phase. So these were dairy production in West Java, beef production in East Java, and pig production in Nusa Tenggara Timur. And each of these systems is very important within these regions, but they also gave us systems that had different types of health and production challenges and had different levels of data quality and availability. So the focus of the presentation this morning is going to be on beef cattle production. And in our case study, we focused on the year 2021, and that was mostly just due to data availability when we started. 2021, importantly, is before the outbreaks of foot and mouth disease and lumpy skin disease in Indonesia. They occurred in early 2022. So if we repeated this more recently, you'd get quite different results. So most cattle in East Java are Bos Indicus Ongol cattle breeds. They're managed in low input, smallholder, cut and carry systems based on crop residues and byproducts. The mortality rates of both young cattle and adults are quite low, and it's reproduction rates that are one of the biggest production constraints in this system. Just a little bit about GBADs quickly to give you some context. So within the GBADs methods, we use a dynamic population model to calculate gross margins at the farm level. And these gross margins are based on the stock value of livestock within the herd, the income from selling animals and their products, whether that's manure or milk or hides, the costs associated with feed, labour, healthcare, and other inputs. And this model is applied to a series of different theoretical scenarios to understand the burden of animal disease. So firstly, the current or the baseline scenario takes data on current animal health, current productivity, current inputs. And this is compared in the first instance to a zero mortality and an ideal health scenario where we change some of these parameters. So in the first instance, the zero mortality scenario, as you might expect, we change mortality to 0 and we leave all of the productivity and input parameters the same. And this allows us to calculate or to put a value on mortality losses. In the ideal health scenario, in addition to no mortality, we adjust the productivity, so things like reproduction rates or milk yields, to reflect a system that's free from animal diseases and other health problems. So the difference between 0 mortality and animal health gives us the value of production losses, and the difference between the baseline and ideal health gives us the total value of health losses. And this is what the GBADs team are calling the animal health loss envelope. So you might hear me refer to this or the ALI later on. So it's important that we acknowledge that neither of these scenarios is practically attainable. We're not saying we can eliminate all diseases and all production problems, but this does give us an envelope for attributing losses to different causes. So whether that's understanding mortality versus morbidity, or infectious versus non-infectious causes, or breaking it down even into specific diseases or syndromes. So within GBADs, we also acknowledge that burdens of disease are more than just an economic problem. There's food security implications, socio-cultural impacts, and environmental impacts. Within the Indonesian case study, we thought we'd do a bit of a first pass of trying to estimate how changes in productivity that came out of the ALI model could impact total greenhouse gas emissions and emissions intensity. And I guess this was a little bit of an exploration to, that hopefully might inform future case studies and improvements to the GBADs model. Though obviously there's a lot happening outside GBADs that we can also build upon as well. So in the long term, it'd be great if we could put something into our GBADs ALI model, and that would give us greenhouse gas emissions. But when we started our case study, the model was still very much under development. I think people would have thrown things at us if we went to them with a lot of requests of, you know, can we just have an equation for enteric methane in there too? So that wasn't an option. Instead, we needed to have something that was available off the shelf. So we went down the route of using FAO's Global Livestock Environmental Assessment Model, or GLEAM, which some of you have probably heard of. In particular, we use their online interactive tool. So this allows you to put a lot of your own data into the tool. It uses an LCA approach with a tier 2 or regionally specific emissions factors for different production systems. The input data is fairly simple. So herd size we took from the livestock census data, and this was consistent with what was going into the GBADs ARLI or population dynamic model. Live weight and productivity, again, was either consistent with the model or was an output of the GBADs model. So we weren't modelling diseases or health as such. We were going, okay, so reproduction changes from fertility of 60% to 70% based on this other model. That's what we're putting in here. It also asked for some quite basic information about the proportion of different feed types in the diet and the proportion of manure that's managed in different systems. And then it has a really, given the simple inputs, has quite a diverse range of outputs. Enteric methane is a big one that we're interested in, but it also estimates some of the emissions associated with land use from feed production, manure management, those sorts of things. And this is just an example of the user interface. So super simple. It worked really well for our team. Nobody needed any modelling expertise or coding knowledge to be able to run this. As well as being really simple, the model had several other advantages. So it allowed us to set up and compare multiple scenarios at once, and it had a nice little dashboard at the end, so we could quickly visualize results and go back and change things. In addition to greenhouse gas emissions, it also calculates how much feed the population of livestock would be consuming and how much meat or milk they're producing. And it also had country-specific default values in the input section, which was really handy in a few cases where we weren't quite sure what to put in. And then the results could be exported as a CSV for people to analyse offline in their own time. It did have a few quirks and challenges. Being an online tool, it did require internet connectivity, which can be a constraint if you're in a remote or under-resourced area or trying to get stuff done on a plane. It was also a bit glitchy depending on which browser people were using. And we had one person whose laptop just wouldn't work for them at all. But the biggest issue was probably around some of the input parameters weren't always very well defined. So the team had to spend a lot of time trying to work out exactly what number they needed to put into the model. And I guess we're still not sure in a few places if we've actually put the right information in. And then with the outputs, there was also a couple of times where what we were getting in the output file was different to what was in the online dashboard. So again, a bit of work required to dig into that and see what was going on. Before I show you a couple of quick results from what we did, I guess there is a little bit of a caveat around this. So what I think is one of the bigger limitations of the GBADs population model is that at the moment there isn't currently a way to constrain herd sizes. So in the absence of disease, if reproduction rates increase, growth rates increase, survival rates increase, the population size is increasing. And depending on the country or the production system, there might be some capacity to manage more livestock and to feed them. But in most systems, there's not going to be enough feed available to sustainably support a larger livestock population. The good thing about GLEAM, since it gave us the amount of feed required for that entire population, we were able to manually constrain the population size so that across all three scenarios, the amount of feed required was the same. It's a bit clunky, definitely an imperfect fix. but for our purposes of testing this sort of analysis, we felt it was good enough. So the first set of results is from when the population was unconstrained. So we weren't putting a limit on it, it was just increasing. First of all, we have emissions intensity. And so as you can see, with decreases in mortality and production losses, emissions intensity was decreasing. However, as you would expect with an increase in population size, there was an increase in total greenhouse gas emissions. The difference between the baseline and zero mortality for total greenhouse gas emissions is quite small, and that reflects the low mortality rates of both young animals and adult animals within these production systems in East Java. That would be very different if you were looking at different types of cattle in other regions of Indonesia where they have fewer resources. And most of the difference here between the baseline and ideal health was associated with improvements in reproduction rates in the model that we then put into GLEAM. If we look at where we constrained the livestock population, so there was the same amount of feed used across all three scenarios, total emissions are very similar between all three. But even though we've got total cattle population isn't increasing, the higher reproduction rates, meaning we've got higher turn-off rates and greater meat production compared to the baseline, and so the emissions intensity is still decreasing. So these results, I guess, were pretty consistent with what we would expect. I'm not going to put my hand on my heart and say they're super accurate, but they are useful as a starting point for us to be able to put some numbers in front of people and to think about how we can improve on this in the future. So I guess just to finish off, our case study has provided an opportunity for us to test out, including greenhouse gas emissions in the GBADs analysis, and do it in a way that was accessible to our Indonesian team. In terms of GBADs more broadly, I think constraining the population growth model within the GBADs model is a huge priority, and I know that the team are trying to work out how to implement this within the model at the moment. And this has implications not just for greenhouse gas emissions, but other outputs from the GBADs program. And then the obvious next step is to work out how we properly include greenhouse gas emissions in the GBADs model. So it's pretty unlikely that we would use a full LCA type approach like they've done in GLEAM, but I think even the inclusion of enteric methane would be a super useful step. Some of the things we need to consider, and Ilias sort of touched on these really nicely, do we use a simple tier 1 type approach where we've got the same emissions factor for all the cows in all the countries, or do we go down the road of having a more detailed model where we're using different emissions factors, if we're trying to account for impacts on feed intake and utilisation, just trying to balance those two things, and also considering if there's other way that, or other interactions between animal health and production and greenhouse gas emissions that need to be considered, and if so, how do we work them into our model? So I'll leave that there. Thank you. Terima kasih.
Thanks a lot, Dai. Very nice presentation. And mentioning dashboards brings me to the last speaker of this session, Angela Bearth. She's a senior scientist and partner at HF Partners in Zurich, and she is a psychologist and expert in risk research from a background. Angela.
Thanks a lot, Reddy. How does the presentation look? All in order?
Yes.
Very good. Thank you. Yes, now something probably quite different, a very different perspective. My role within DECIDE is the lead of the Work Package 5. The Work Package 5 is very much focused on our stakeholders, farmers, veterinarians, other people working in animal health and welfare. And so our perspective as mostly psychologists was to understand what kind of needs users have when it comes to dashboards for making decisions about animal health, and also to understand a little bit how we can make the tools that are being developed in DECIDE address these needs, but then also the design of these dashboards. So a lot of my research focuses on the one hand on objective risk information about likelihoods, about severities of outcomes and so on, and how this translates into human minds. How do people make sense of these numbers? And when I say people, I mean experts as well as sort of lay people within the field, which comes down to what the users of the dashboards are in the end. And one of the first things I would like to talk about a little is the translation of data into information. So very frequently, us researchers, we love data. We love looking at dashboards and vast amounts of just information, and we try to make sense of it. But in order for information to become useful for decision makers that aren't necessarily so happy about data, it needs to be filtered, it needs to be translated, condensed into sort of a set of relevant information. And what I also want to talk about today is a psychological construct, the construct of cognitive load. Cognitive load means how much are we already focused on something, how much are we distracted maybe from a decision, how much cognitive resource, mental resource can we assign to a certain decision. And if we think about everyday life on a farm, there's a lot of cognitive load to deal with. So ideally, a data tool does not add to this cognitive load, but rather supports it or even reduces the cognitive load. And that would really cover some of the users' needs as we have assessed in our project. So this is a very simple slide that pushes together a lot of research that has been going on in the last few years. Xiao Zhu is also here, our postdoc who has done most of this research. So for example, we did all over Europe, we did focus groups with farmers, with veterinarians and other stakeholders in animal health. And we basically discussed with them what their needs were when it comes to this data, when it comes to translation of this data into information. And this is sort of what it boiled down to, the conclusion of these interviews. So on the data side, we have a lot of challenging things that need to be fixed. First of all, the data needs to be predictive of the outcome that we're trying to model or that we're trying to have the decision makers understand. They need to be spatially and temporally relevant. That sounds very broad, but that's really something that came out of it, that it's a challenge to really have temporally relevant data. Ideally, these should be automatically updated, but many data that is predictive of the outcome is not necessarily so easy to automatically and have data that comes in at the right time where the decision needs to be made. It needs to be highly reliable and then, of course, highly valid. So it needs to, the data that goes into our models needs to be valid for the outcome that we're trying to predict or model. And then also there needs to be a bit of a reliability depending on how the input of the data is being made. Is it farm workers that put the data in there? Is it clear how it is inputted and so on? So all of these on the data side. As if this wasn't challenging enough, we now have to do this translation of the information. We need to contextualize it. So that was something that came up very frequently. For example, when we talk about mortality in fish farming, mortality numbers alone weren't seen as so helpful from most of our stakeholders, but they rather would have liked this to be contextualized with some other data points, with some other information, such as the reason for the mortality, or then also sort of a perspective over time, the possibility to benchmark it against other farms or other regions within the farm. Personally relevant, so that was also a little bit of a challenge, I suppose, when the data that is available that can be translated into information might not always be the ones that answer the questions that our stakeholders have. So that there needs to be a bit of a match there as well. Then we have the whole design part of the dashboard. It needs to be comprehensible. The information needs to be comprehensible. So which mortality is actually reported? How much explanation does the user need of how this mortality is calculated? And then we also have sort of this user friendliness, convenient and intuitive in its use. So all of these things need to be fulfilled in order to have a really well-working dashboard. And since I've said at the beginning, my work is very frequently focused on the topics of uncertainty, complexity, and risk. And we do have these topics within animal health. So I would like to talk very briefly about all of these three. So the uncertainty associated with the use of a digital tool, we have certain points that lead to uncertainty in terms of the user of the tool. So in our simple model of translating data into information, everything that goes into the data is associated with some form of uncertainty, but also perceived uncertainty. So if a user of a tool perceives the data collection to be not so well made, or feels like the data is not necessarily valid, the tool is not being used, and the tool is also not seen as very beneficial. Even if the data collection is in fact quite reliable and valid, we need to think about both these levels. So the perceived uncertainty, the perceived, maybe the confidence in the tool, but also the actual confidence that we should have in the data collection. Same for the preparation, so the modeling of the data, or how the raw data is then transferred into certain predictive information. The translation also is associated with some uncertainty, so it relates to the amount of information that you give about the data. Is it really just an early warning ping that comes to your phone and you don't get any other information? Or is it a vast dashboard that gives you loads of information and explains how each of the data points have been gathered? So that's a decision you need to make when you think about creating such a dashboard. And then some things, what we also always try to focus on in DECIDE is not just the information, but then also how does this actually lead to the goal that we're trying to achieve? So better, faster, more efficient animal health management. And that's also associated with quite a bit of uncertainty. So what do people actually make of the information that you're showing to them? And I'd like to talk a bit about this in the next sector. So now I would like to focus on the complexity. We've seen in the previous talks, as Gerdien has also said, it's not always that easy as you first think. And when complexity meets with a human user with their cognitive processing, then it's good to sort of think about the two modes that we use. I always like to equate the human brain as a highly efficient machine. If we have currently the best supercomputer worldwide, that sort of has the same information processing capacity as our brain. So we are capable of dealing with very high cognitive loads. This is when we use our analytical system. It is as a rather slow system. It's very resource intensive, so we need to focus. We need to put a lot of resources into it, mental resources. That's when we're dealing with facts, statistics, when we're looking at data, analyzing data, interpreting data, when we're weighing up pros and cons of certain measures that to be taken on the farm. And as I said before, this really requires a high cognitive load. Because we're a highly efficient machine, we also have a mode of decision making that isn't focused on isn't so resource intensive. And that's our fast, or sometimes also called automatic system. It comes into play when our resources are scarce. That means when we have very little time, very little mental capacity because we're focused on something else already, then we use this system, and this also comes along with a lower cognitive load, but it has the certain risk that because we're not using our analytical system, it might be prone to biases. It might be prone to decisions that are then maybe not in the best interest of the animals, not in the best interests of our farm. So during our day, we're sort of always in parallel using these two systems. So it's not that we're activating the analytical and then the automatic is off, but we're sort of leveraging our resources by either making decisions with the analytical or then with the automatic system. We asked some questions to our stakeholders in the DECIDE project about whether what they feel like day-to-day decisions about health and welfare are more reliant on the intuitive or more reliant on the analytical system. And we can see here a very big variance in responses. So here we focused on broiler farming, how day-to-day decisions are made on broiler farms. And you can see that they're sort of here in the area of a large portion being made intuitive and then some analytical. And that has implications for our data tools. So how much cognitive load can we require from our stakeholders if they rely their decisions mostly or to a large portion on intuitive, on the sort of fast track mode of thinking. So we need to be able to predict how they deal with the information presented in the tool, but then also to ensure that there's no biases that then lead in the end, despite all the good data that goes into it, despite the well-translated information shown, but then the way this information is translated into decisions is in somewhat biased. In this topic, so the FAST system very frequently relies on heuristics, and I just briefly want to give you a definition or an explanation of what a heuristic is. So if we're presented with uncertain or ambivalent information about a risk, about a decision that we need to take, we could go the slow route. So the analytical mode of thinking, we can do evaluations, assessments, we can think about things, we can come to different conclusions. And then in the end, we have our judgment and decision. That's resource intensive. So heuristics help the automatic system to come to a sort of shortcut to the decision without having to make all these evaluations and considerations. We use the heuristic. So it's like a rule of thumb to come to a decision. And I just want to give you some examples of heuristics that are at play in this area. We have on the one hand, because we're dealing with, in very frequent cases, we're talking about quantifying health outcomes. We have numerical data presented, and we have here an example of one of the tools from the DECIDE project, and it allows here to see your own farm and compare it to a national average or the national median, and then it also gives you a bit of a scoring system in a color coded way. So if you're in the green, that would sort of give the information that you're fine. If you're in the yellow, maybe not so fine. So you have different things where you can anchor your decision in. And if you think about what kind of message you're sending, so if, let's say, assuming that this is not necessarily a good number here for the farm, but it is still below the national average, you're probably going to give the information to the user, give the anchor to the user that everything is perfectly fine. So you really need to think where you're setting these anchors to help people make decisions. So the color in this case is acting as an anchor, as well as the national average and national median. The optimistic bias, I sometimes call it this is fine bias. So we humans tend to underestimate negative things happening to ourselves or then to our farm in this case. So that's something you need to think about when you present information to overcome this sort of optimistic bias. And if you really want to warn people. So if the goal of the tool, if a piece of information should act as a warning or then a call to action, then you need to overcome this. This is fine optimistic bias. And then framing effect is a very old heuristic that has been very well researched. Depending on how you frame a piece of information, people might decide differently. So if you have the information, by treating this cow now, you have a 90% chance of preventing further complications and maintaining herd productivity. That will likely spark more actions than if you have the information. If this cow is not treated, there is a 10% chance it will develop severe complications. So it's basically the same underlying data, the same piece of information, but it's framed in different ways. And data suggests that people then are more drawn to the first piece of information than the second one and will be more likely to act upon it. There's many more of these heuristics that are at play when we're presented with uncertain information to come to a sort of low cognitive effort conclusion. And then lastly, I would like to talk just briefly, because I mentioned it already, about the risks. So very frequently, the information presented in data tools gives some information about a risk, about a likelihood, about the uncertainty. And I always, in my work, you have the objective risk, and then you have what people make of this objective risk, of the available information about this objective risk. So you have objective risk and you have risk perception, and both have implications for behavioral outcomes, for decisions taken based on this information. So if you have objective risk shown in a decision support tool, mortality, likelihood of outbreaks, this is translated within the cognition of the users of your tool, and you should make sure by evaluating your tool well whether this translation works fine. So if it really indeed sparks the risk perception that you want to spark with your information. Goes with this example that I gave before. If you highlight something in green and you really feel like this should be a warning, this should be people reacting to the information, then you might want to go into the orange and really think about where you set these anchors in order for this translation to work well from objective risk information shown in the tool and the perception elicited in the user. And then lastly, you should also test whether the behavioral outcome is there. Thanks a lot for your attention and for inviting me, and happy to get into any questions.
Thank you, Angela. Interesting also in relation to this greenhouse gas emissions and the risks that we see there, I assume. So far, there are no questions yet in the chat. Are there any people that have questions? Feel free to speak out when you have a question for one of the speakers. I don't see any hands yet. Okay, so Dai, I was thinking about your analysis with the diseases and with the zero mortality scenario and no disease scenario, and you mentioned that they are not realistic. And then you show how much more emissions there will be. So, and then given Angela's talk about numbers having to be realistic before people start believing it. So how will you deal with that? The non-realistic scenarios versus how are people going to deal with your numbers that you produce?
Yeah, that's a great question, and I think it's been the one thing that's been most hotly contested within the GBADs program for the last 5 years, if not more. I guess I tend to be one of the people who my personal preference is to use an attainable yield when you're measuring productivity gaps. I guess depending on the audience, and if I tend to work more directly with industry, they want to know, what's realistic for me to increase my productivity to. So for them, a regional benchmark of productivity might be more useful. And so these scenarios that we've kind of settled on as common between case studies, the zero mortality and the ideal health, I guess we do have to be very careful with how they are communicated. I think from a theoretical perspective, they are useful in us defining boundaries of what that loss is, and then being able to break it down and go, okay, well, this much could be due to nutrition or heat stress. This much could be due to brucellosis or other infectious diseases. So it is more of an academic perspective. yeah, I think we're always evolving and learning with this. But yeah, I think Angela's messages are really important for us, and they kind of fit with what a few of us have been thinking for a while. So always good to have that reiterated. Thank you.
And I see Ilias has a quick response. Ilias, I can't hear you. The sound seems to be lost. Am I the only one not hearing him?
No.
Yeah, now we can hear you.
Okay, apologies for that. It's a kind of a comment today, but also linking Angela's talk. When it comes to the impact of animal health to greenhouse gas emissions, there is a cognitive bias, which actually I think it's people want to believe that there is a link between animal health and greenhouse gas emissions. And there is no doubt why they want to believe that. But at the same time, they would believe any kind of numbers you throw at them. And at the same time, quite often, people know that the methodological approach is wrong, but they do not care because all they need is some numbers. And I have found that out in my dealing with stakeholders. And I wanted Angela's response to that, because people know that the numbers are wrong, and yet they want to believe them.
Angela, can you give a last response? We're going past time a little bit, but it's interesting.
Yeah, I guess the question is, who are the stakeholders? So do the stakeholders have some degree of knowledge of the data, of what the data means and what the methods mean and so on? I think there's probably a different response depending on that, because when it comes to our farmers, they are experts for their animals in many cases. And then you have to sort of deal with this. I have a feeling about it, or I have a knowledge about my animals, and then some data is shown. But then on the other hand, if you have lay people, if you have consumers, that's also something we discussed in DECIDE. So what does it mean if we suddenly make mortality dashboards publicly available? What will people make of these numbers? How will they be used? So that's something that is always in the background, I suppose, that you have to foresee and maybe collect some data to make sure that you don't have backlashes when it comes to this.
Okay. Seeing that we are 2 minutes past 11, I think we need to close the discussion here. I want to thank the three speakers for their excellent talks and a nice discussion amongst them. I'd like all the people that attended this webinar for their attendance. I hope you saw something interesting. I at least learned a lot. There will be a next webinar in about 2 months, and you'll be posted on that by Hannah, I'm sure. Thanks everybody, and see you next time, I hope.
Bye all.
Bye.
Bye.